When we have an expression like this with a lambda form in the body of a let, then what should happen is that this expression 10 gets evaluated and bound to y and conceptually substituted in for y so that the result should be the same as the function take an argument x and add 10 to it. To make everything fit on the next slides, I'm actually going to write it all on one line, but it's the same thing. The thing about this substitution view, though, is it's not how our interpreter works. Our interpreter actually works with deferred substitutions. So let's look more at how things work there. Here I have interp with this expression, and the second argument to interp is an environment, but I'm showing that as a bubble attached to the expression. We start out with no bindings, but as we go inside the let and start evaluating the body of the let, then we'll have the substitution that says y equals 10. So together, it's really this function expression and the environment that define the function that we should get back. Let's see how that plays out in a larger expression. Here I've got an interp of a function represented in the blue box here applied to a value represented in this blue box. So you see this curly brace right here, that's a function called curly brace. Everything in blue is supposed to reproduce the function that we're applying, and everything in blue now is the argument to that function. This function takes an x and adds x to y where y is 10. So it's going to add x to 10. This locally lets y be 7 and just returns y, so this thing produces 7. So we're passing a 7 into a function that adds 10 to its argument, so the overall result should be 17. When we evaluate this application, then we're going to evaluate the argument and the expression and the function. So when we look at the argument expression evaluation, we know how that works. We interpret this let form, we bind y to 7, we end up evaluating the body y with interp, given the environment y is 7, and so we get a 7 out. When we evaluate the function expression, it's very similar. We have a let form with y is 10, so we start evaluating the body, lambda with y equals 10. And now we need to return a function, and we still haven't sorted out how to represent a function. In the case of a number, notice that we could just ignore the bubble. We didn't need to know anymore that y was 7 along the way. In this case, however, we need to return a function that takes an argument and remembers that y should be 10 when we start evaluating the body. Right? The function hasn't been called yet. When it's called in the future, we need to remember that y equals 10 to add to the given x. So the information we need to remember is this bubble, the body of the function, and also the function's argument name. We don't need to know that there was a lambda and that this curly brace was here and so on. That's always the same. But the parts that vary are this name, the body expression, and the environment. And we're going to put those three things together in a value called a closure. It's called a closure because it closes this expression with respect to a set of bindings. That leads us to this representation of values, where we have the distinction between numbers and closures, because numbers and closures are both kinds of values. In the case of a number, all we care about is the actual number inside. Note that num_v constructs a value that's a number, whereas num_c constructs an expression that's a number. Close v then is a closure, which has those three parts, the name of the argument, the body expression, and the environment. Meanwhile, we change our definition of binding to map names to values instead of just to numbers, since we have more kinds of values now. So given this representation of values, when we interp the expression 10 in the empty environment, what we expect to get back is the value 10, which we write as num_v10. So this parse of 10 here produces num_c10. The interp of a num_c produces a num_v. When we interp an expression that has a lambda kind of result, then we get back a closure, because closures is how we represent functions as values. Again, the closure has three parts, where the name of the argument in this case is x, the body is plus xy, or really the parsed form of that, right? So it's a plus c. And then the environment at the point where we get to this lambda form, it maps y to 10, and it's y to, again, the value 10, not just the number 10 here anymore, but a num_v10, since names are mapped to values in the environment. Going back to our application, remember we were applying this function to this argument, and we saw that when we get to interpret y, we had y equals 7, but I'm updating that to say y equals num_v7 now. so that the argument produces not just a plain 7, but a numv7. The function, we got this far, where we had a lambda form and we had y equals now numv10. And so I'm saying that the result of interp of a lambda function, a lambda form, that is a lamc, should be a closed v. A numc produces a numv, a lamc produces a closed v. Right, and the closed v has the name of the argument, the body of the function, and the environment that we had at the point that we got to the lambda, which is just the PLAI typed representation of this bubble here. So the application form applying this function to this argument would have recursively called interp and got these two things back. And since it got this value for the function part, it wants to work on the body of this function now, substituting in this value in place of the argument x. In other words, we're going to have a recursive call to interp on the body, which we pull out of the closure. In that body, x, we know the name is x from this part of the closure, should be mapped to this actual argument value numv7. So we add that to the bubble here, which corresponds to adding it to the environment argument of interp. In addition, though, that environment needs to say what y is, because as we interpret this, we're going to get to y. In other words, we're starting to interpret this body, we need to remember the substitutions that apply to that. That was saved with the closure. So we're going to take this environment and use it as a starting point for adding in a binding of x. That is, we take this bubble, and that's the one that we extend with x equals numv. From this point, you can see how interp will interp a plus expression, evaluate y and x, and get 10 and 7 and add them up to 17, as we expected.